So I'm actually one of the founder members of the European Materials Modeling Council and have had many interactions with the project officer who was pursuing these ideas on multiscale models. So I'm somewhat known in the halls of the Commission in Brussels. And I'll be talking about that because that's the angle where I come from, and I would say perhaps slightly unusually in this particular event. So I'll just mention how we look at perovskites, looking more as much top-down as bottom-up. In other words, looking from device level down in length scale. But I'll spend a lot of my time, as I said, on organic device modeling using the kinetic Monte Carlo method, in which Jarvis and I published a paper which I'm still really proud of some years ago, early days of multiscale modeling, using kinetic Monte Carlo methods. So first of all, to illustrate the point of length scales, I don't know if any of you would like to hazard a guess of what this photo is of. It was taken by David Cairns' wife. Followed? It's not a bad guess, actually. Yeah, it's actually sand in a beach. It was in September, and we were at a summer school for Maestro, which is my training network, which I coordinate. So yes, but that's exactly the point. Yes. So multiscale models. So this is the European Union officially permitted multiscale model description. It's actually not bad, and the bus took a lot of input from a lot of different people. So it's the standard description. We start at electronic net scales at angstroms, move into hundreds of atoms, nowadays thousands of atoms, and eventually end up at the device level, which is the continuum models, which the engineers like. And in the middle, we have the mesoscopic models, which has been a rather neglected area. So I'm going to, first of all, discuss how we look at perovskites at this intermediate length scales, which is, I'm talking about here, tens of nanometers, because I think it's really important to kind of be able to talk to the engineers and relate your atomistic models to their device performance. So my group has been active in all these length scales. I was working with Saiful Islam, and we had a postdoc, Debia Ghosh, who did a lot of really, really nice work looking at how you've got this very soft material and how the cations in a perovskite move around like nobody's business, and how their motion couples to the cage of the lead ions. And you can use that to explain a lot of, for example, optical properties. Then I also have spent a lot of time at the device level, and with Giles Richardson's group at Southampton, we developed this model which explains hysteresis, which I'll come back to in perovskites. But I won't spend very long on it because that's really nothing to do with polarons. It's just about having some charge carriers, whatever they are. But they're also coupled to ions, which move around. But I'm going to spend most of this part of the talk talking about our mesoscopic modeling, because that you really do have to think about polarons. So just a point for those of you who aren't so familiar with perovskites, and this is a point that also Jarvis has made and others. The perovskite lattice is very soft, it's very deformable. And in fact, it's 2 orders of magnitude, small lower bulk modulus than steel, just to ram that point home. It's got this classic structure, which was produced by Chris Eames' diagram, by Chris Eames in Saiful's group, which shows nicely how you've got these octagons with the lead iodide, and in between these octagons you've got these cations, which are often organic cations, but not necessarily organic cations. Okay, and the point is that these things wobble a lot, to use a nice scientific term, and Jarvis has also talked about this a lot in his papers. So Jarvis mentioned recombination. Why do we care about recombination? The answer is because we want our solar cell to work. And so what we have is that the way the solar cells work is you excite an electron across the band gap to create an electron-hole pair. Because in the case of perovskites, you've got this very high dielectric constant, the exciton formed very, very quickly dissociates, and you get the free charges moving out of the cell in different directions to create a current, and on the way out of the cell, they can recombine. Radiative recombination is fascinating, but it's not so important for a device person because the photons that get emitted simply get reabsorbed. But non-radiative recombination, on the other hand, is important because it reduces the open circuit voltage. The other point is that, I was lucky enough to work with Henry Snaith in the dye-sensitized cells day, so I was in on the ground floor with perovskites, and Henry was mushering for years about this hysteresis, and we established, Giles Richardson and I really established at a very early stage that we could show how it was due to the motion of the iodide vacancies. So I'm going to talk this fairly quickly because I really want to move on to the organics work as well. But just to say that we set up, with Giles' group, we set up this code called Ironmonger. And if anyone is curious and wants to work in this area, you're very welcome to download it and email me about it. But it shows very nicely how the ions move as you apply an electric bias across, and as they move, they screen the electric field, and that changes the current in a nutshell. But again, I don't want to dwell on it here. Now, coming back to our picture of the beach, this isn't a picture of a beach, this is a picture of a perovskite, and they're very multicrystalline. So you will have seen in Jarvis' talk that he predicts these very high mobilities. And one reason why the mobility is so much higher than experiment, we're talking about 1 or 2 orders of magnitude here, is because the perovskites are polycrystalline on a length scale, on this mesoscale of tens to hundreds of nanometers. And this lovely picture by Sam Strank's group. Sam is in Cambridge, and we're working with him to try and understand his experimental results. But this shows how you get grains at many different sizes. And so you've got to have a mesoscale model to really understand how the grains are affecting the mobility of perovskites. It's quite controversial because some people say that they make no difference. We believe they do make a difference, we being Matt and me, or really Matt, and I just follow what Matt says. But anyway, the point is that you get this fascinating multicrystalline material. Okay, another interest, which Jarvis also alluded to, which I find very interesting, having worked in solar cells for many years, is the hot carrier solar cells. And to illustrate, this is where the Polarons come in. So all you wake up, it's Polaron time again, right? Because, why? It's, you excite your electron across the band gap, fine. It's generally got an energy bigger than the band gap, and so it has to relax once it's in the conduction band. And how it relaxes is determined by the polaron nature of the carriers in perovskites. And you see, nicely, this is Maria Loire, who's an experimentalist in Groningen, and they produced this very nice review showing how the energy distribution of the carriers, the electrons and holes, evolves with time as they cool. So why is this of interest? I have a technologist in me, largely because that's the best way to get European funding these days. What you do is you've got these hot carriers, and the energies allow some of them to get extracted at the electrodes with a difference in the quasi-Fermi levels. That's the Fermi levels you have in the presence of a bias. They're not true Fermi levels, of course, but they represent the fact that you've got local equilibrium. So you get away with defining this quasi-Fermi level, and the difference between the quasi-Fermi levels at the two electrodes is what gives you your output, your open circuit voltage. So you can see from this diagram that you're going to get a bigger open circuit voltage if you get hot carriers than if you don't. So years and years ago, before most of you were born, there was a very nice technique invented by Alan Boardman and Richard Hockney and others for looking at submicron semiconductor devices. Well, inorganic semiconductor devices went out of fashion in the late 80s because the production moved to China and people lost interest in research. But this beautiful technique was developed which allows you to track the trajectories of the electrons and holes by a standard Monte Carlo trajectory method. In other words, you have the carriers moving in K space and momentum space. They're wave packets, so they have a spread of momentum, but they have a reasonably well-defined momenta at the center of that packet. And when momentum changes as the carriers scatter off phonons and impurities and grain boundaries. And because it's wave packets, they also have an approximate position, and you can keep track of that and follow how the dense particle density evolves with time. So Matt will be talking about this in much, much more detail, say the last talk on Thursday after Annabella Saloni's talk. But to cut a long story short, Lewis, my graduate student, and Matt have produced this predictions, which we'll obviously talk with Jarvis about, but I don't think we really, I don't think we quite, I think we're fine. We have to talk to you, Jarvis. I don't think we contradict you particularly in what we're doing. In fact, I would say we actually agree with you, but we need to sort out the details. But anyway, the point is that you've got the mobility variation with temperature is very similar for the polarons, which is formalism that Matt did. He showed how the carrier scattering rates differ between polarons and free electrons. And you can see that it actually makes very little practical difference in terms of the exponential in the temperature dependence. But nonetheless, this is early days, and we're working hard to see if we can come closer to experiment. But I think the point we want to make here, again, will be emphasized in Matt's talk, is that people were arguing that the difference between the measurements, which I show here for the temperature dependence and mobility, and the theory, which was just for free charge carriers, was because, in fact, they were polarons. And these results show that you've got to introduce more than just polarons to explain that discrepancy. So more work to do. So now I want to move on to organic devices, which, say, Frank introduced in his very nice talk yesterday. So for those of you who don't know how organic solar cells work, you excite your electron hole across the band gap, as you would with any inorganic semiconductor, but they form the excitons. The excitons are very tightly bound in this case, bound by half an electron volt. So they move through the material as excitons. They cannot be dissociated by thermal excitation. And the only way you're going to prise the electrons and holes apart is when the exciton finds an interface between two materials, at which point it gains the energy to dissociate. And you can, your separated charges, if you're lucky, will find their way out of the device and create a current. If you're lucky, that's referring to the fact you will get a lot of recombination. So this is work I did years and years ago, but it's what I think kind of I'm still find quite helpful in determining the mesoscopic physics of organic devices, done by a graduate student of mine, Pete Watkins, back in 2004. Anyway, the point is that it shows very nicely results which at that time were not understood, which is that people make polymer blends. They discovered those work better, but they didn't know why. And we showed that if you have a blend, firstly, if it's very coarse blend, then the excitons move through the material, but they don't get to an interface where they can dissociate, so they recombine. So you get a very low current. If, on the other hand, you have a very finely mixed blend, the excitons, surely they dissociate, but they become a bit like Harry Potter wandering around in that maze in one of the films and being beset by all sorts of demons. And in this case, the free charges recombine. Most of them recombine on their way out. So you've got to have this sort of happy medium, which is domains which are of the size and exciton diffusion length, and that will give you a maximum. And yeah, so that way we use the kinetic Monte Carlo, which was been around, was been in surface physics. In fact, it was in a paper on surface physics that I found out about this method. Okay, so now, what about polarons? So the point is that in organic materials, the charge carriers are polarons because the molecules deform very easily to create the self-trapping effects. And again, what I think of always is length and timescales. And this point was alluded to yesterday as well, that if you've got static disorder, that simply means that the disorder is evolving on much longer timescales than timescales you need to get the charges out of the device. And typical hopping rates are of inverse nanoseconds and higher. Phonon frequencies, on the other hand, are much higher. They're typically terahertz. And so there is a timescale difference. And so what we do with our Monte Carlo methods is we assume there's a lot of static disorder that determines how polarons move, and that is the picture of charge transport in organics. Now, as you can see from these scales, there is overlap where it's neither fish nor fowl, to use an old English expression. It's neither dominated by static disorder, nor is it fully dynamic. And that, of course, is Murphy's law will tell you that's where organic devices operate. So we've got to worry about the fact that you can't just treat disorder as static. And again, this was alluded to yesterday. But as a rough, just to get a model going, we do treat it as static. I'll show you why, how and why. Because the energy associated with the changing of molecular conformation is about an electron volt, compared with the reorganization energy, which appears in Marcus theory, of about a tenth of that, which is what determines how the charges relax in the molecule. So this is a picture due to my graduate student, Alex Smith, who is sadly, nicely for him, but sadly for me, recently got his PhD and has now moved on to MATLAB, to math work. But anyway, what we do, the way that I think of the universe, is as a series of hops. And here I'm showing them on a lattice. We, in fact, do a lot of off-lattice work these days. But the basic idea is that you calculate the variance of kinetic Monte Carlo, you calculate rates to all possible sites, you can then calculate probability of hopping by selecting a time period and determining which hop you do, and then you move the particle according to that determined rate. That's a succinct summary of the whole of kinetic Monte Carlo, at least as we know it. But, as I said, morphology matters. And this is a picture I took from a Science Reports paper, and it shows just how horrible, or at least horribly complicated, the organic molecules are, organic films are, because you've got all these molecules very close together in a film, and the hopping rates depend very, very sensitively on the relative orientations of these of neighboring molecules. So Ian Thompson, who is also sadly moved on, he was funded by XMOS, which is a project I coordinated until it finished this year. And with Claudio Zanoni from Bologna and his group, and David Beljean, we did a multiscale model, but what we did was we looked at charge transport we compared it through these columnar morphologies, which you get with these discotic liquid crystals, and we then compared that with charge transport when you heat the films so that they become disordered. And not surprisingly, we see a lot of angular variation in the transfer rates in the columnar phase compared with the amorphous phase. But really what this does is it shows that we've got, our theory at least gives the right intuitive behavior. So Ian developed a nice way of measuring the charge transport by looking at flux integrals. And you could see here that you've got, in the columnar phases, you've mainly got charge going up and down the column, but you do have some motion between the columns, and this kind of quantifies those effects, whereas in the amorphous phase, you just get charges hopping every which way. But again, we could quantify it and calculate mobilities in these cases. So now I want to move on to much more recent work, keeping an eye on the time. So mathematicians at Bath is Eike Müller and Will Saunders, and Will is a postdoc now in my group, also still working very much with Eike. And they adapted fast multiple method, which is a very well-known technique to mathematicians, but they adapted it to the kinetic Monte Carlo algorithms. And I don't want to go into detail because I'm running out of time, but gladly answer questions about it. But they could calculate the energy change of a hop. Now, it's much quicker to take your landscape of particles and calculate Coulomb interactions, and then start off doing it once, and then after that, you just calculate the energy changes with each hop. And it's much quicker to do that, recalculate the energy of the whole system at each hop. That comes under the blinding the obvious, but the way it was implemented with this fast multiple method is very far from blinding the obvious. And they did some very nice, elegant work to greatly speed up our kinetic Monte Carlo simulations. So we can now do 20,000 particles. This is a real bottleneck for kinetic Monte Carlo because it just took so damn long. Now, thanks to this fast electrostatics, we can do it. You can do it in your smartphone in half an hour, kind of thing. It's made a big difference to how quickly the code runs. It runs off lattice. So in other words, we can look at the molecular packing arrangements as well, and we believe that to be very important. So we now can include the long-range component, which was rather blatantly and neglected in a lot of papers on kinetic Monte Carlo in organic materials. So the conventional way, and a very nice way, developed, decades ago by Bessler and others, and Arkhipov, is to describe particles moving in a landscape with Gaussian fluctuations. But that's a kind of mean field approach. And the advantage of Monte Carlo, kinetic Monte Carlo, is we can go beyond that. And we can allow for the fact that the charges will move as they see local electrostatic effects. So how much longer do I have just to make sure I don't go over? Is it 10? 10? 5 minutes. 5 minutes, that's fine, that's fine. So the point is that Ian, it's rather dark, which is annoying, but you showed that at very low dopant concentrations, the charges will get ionized. This was, they're fully ionized. This was beautiful work done by Xavier Blas and others in XMOS to show that the dopants in organic materials are contrary to what had often been stated. They are fully ionized, but the charges never get away, the ionized charges never get away from the dopants because of their strong electrostatic attraction. But as you increase the dopant concentration, even still at quite low concentrations of 1%, the landscape merges, sorry, the potential wells merge to create a much flatter energy landscape, and that allows the charges to move much more freely. So this is really just summarizing what I've just said, so I won't. So the point is, again, just to stress, the doped systems create these fixed ions that frustrate the system, distort the landscape, and in the process, they create a new energy scale. And so the whole point of going to all this effort and computing time is that the Gaussian disorder models simply don't work when you've got this new energy landscape introduced by the dopants. Okay, so I'm just going to just say that if you assume the free charge carriers are always free and always immediately free once the carriers get ionized, you get the wrong doping dependency of the current. And you also get the wrong doping dependence of the charge mobilities. Okay, now I want to move on quickly to polymers, and this is just lots of pictures, but I think it's quite important. It's been an area that's really been fascinating me, largely because it is very, very difficult. And my parents used to say that was characteristic of me, that I used to like to go for difficult things to do. Anyway, the Noriega, Alberto Soler, and those guys had this picture that polymers have this disordered, consist of disordered aggregates, regions which are semi-crystalline, linked by what's called tie chains. Because the point is that because charges travel very quickly along the polymer chains, about 2 orders of magnitude faster than between the polymer chains, it's these tie chains that dominate the conductivity of the polymer. But they also point out you get a lot of polymers which are completely amorphous, and they couldn't really explain that. And the thing is that the recent polymers developed by Ian McCulloch and others, and being tested by Henning Seringhaus, they're very, very high mobilities, but they're completely amorphous. So why? So this is work done by Alex Smith, who's my student I just mentioned, and he was able to develop a way of doing molecular dynamics, a kind of heuristic molecular dynamics that allows us to look at very large systems. Alex motto used to be go big or go home, and he exemplified it by generating these large systems on the back of a cigarette packet. In other words, again, just on a standard single processor workstation overnight. I mean, it's very, very fast, but you could generate these morphologies. And what you could find is where the polymers come close together. And that's important because the charges, our view is that the charges move rapidly along the polymer chains until they come to a point where the chains come close together, and at that point, they've got a relatively much higher probability of interchain transport. And so charge transport in polymers is dominated by this effect of mostly intra-chain hopping with the occasional interchain hop. And this ties up nicely with recent work by David Barjon and his group, and Henning Sirringhaus' group in Cambridge, looking at OLEDs made of these polymers, which show that you get bright spots at these crossing points. So I think I'm going to skip this lot because I'm run out of time, but Alex showed very, in a way, standard stuff, but he applied it very neatly to this problem to look at, solve the master equation to get at the polymer, the charge diffusion coefficient in a polymer film, which allows for this very much faster in-charge chain transport. And we used, and by the way, those of you who don't like Markov theory, these were the crossing, the transfer rates were determined by proper quantum chemistry rates by Johan Olivier at Mons. So, but what's nice is we can now predict the diffusion coefficient as a function of the rate at which the charges move along the chain. So, summary. So what I've got is, I would argue that multiscale model gives you a whole different perspective on modeling, on life in general, and in particular for understanding how cell performance is related to atomistic theories. Because by bridging the length scales, we can look, and the nice thing is that we can look at charge transport across the device, but we can also understand the effects of defects and interfaces, and we're heading down the grain boundary route here in terms of future work. We can allow for the loss of free charges due to recombination, because that is nicely modeled in a Monte Carlo approach. And we can include the excited states with all the nice theories being developed by Xavier Blas and others that allow for excitons as well as free charge carriers. So I really would like to thank my group, Matt, look at, I have to say, this is clearly a warmer day, a warmer place, but he's sitting at the back, so you're very welcome to talk to Matt. Ian, who got a nice job in industry. All my postdocs get very well-paid jobs in industry. Anyway, but he did a lot of the work on the Monte Carlo. Lewis is still working with us, I hope. We'll be back when we get back. But we'll, unless he's pushed off for Christmas. But he's done the work with Matt on the Polarons. And also Dibya, I mentioned, and Thijs is looking at the grain boundaries, and Alex I already mentioned. And Will is just the math genius that we have, fortunately in the same office. So I'd like to thank you all for listening.
Experimentally, how is it measured that they relax slowly?
Okay, that is a good question. So I think the way they do it is that you can excite with very fast spectroscopy. So you can look at, for example, you can femtosecond spectroscopy. So you can see how the photoluminescence evolves with time as the charges move around. And the advantage is that we're looking at very fast timescales. You can identify where the charge motion is just determined by the behavior within a microcrystallite. But coming back to hot electrons, well, at these short timescales, again, the charges are hot. So if you can predict the time dependence of photoluminescence, then basically you can only do that with a model that allows for the hot electrons.
Yes. You said in the case of the perovskites that something is missing to get the mobility right.
Yes.
Would it be the defects of grain boundaries, or do we have them already?
Well, that's exactly the point, that we do think it's a defects of grain boundaries, but we already are trying to excuse me, incorporate them in the model, but we haven't done so yet. The reason it's controversial is because the grain boundaries are known not to be very strong not to be very strong scatterers of charges. But we still believe that because there's so much scattering, even though it's not move the charges through great angles. It still has a strong effect when you allow for lots of scattering events. But really, it's unknown. And the other point about the grain boundaries is they're full of impurities and stuff, and those will produce much stronger scattering. So ask me in 2 years' time, and I think we'll be able to provide a better answer. Well, precisely. So that's the, well. So we we take this kind of more, shall we say, approximate view in the sense that even the band electrons, we think of as being wave packets. So they're not really hopping. Of course, they're just scattering. But the point, when they get to the grain boundary, of course, they have to move through a potential barrier, or at least cross a potential well. It's not even known, this is what I find really interesting, to what extent these grain boundaries are barriers or wells. But for sure, you've got the right essence of it, that they, in a sense, the way you could argue the wave function collapses, and they behave a bit like a classical particle, which then hops across the grain boundaries. But I think, but it's totally dominated by what's at the grain boundaries. If you just have a pristine grain boundary, almost if you can imagine such a thing, in a pristine, otherwise pristine material, I don't think the grain boundary will have a huge effect. But you've got a grain boundary that's full of trapped ions and has a lot of defects, then that's going to have a big effect on whether the charges can get across. Well, yes. Well, so I think all I can do is, the short answer is no, but what is known about grain boundaries is probably best encapsulated at this nice picture of Sam Strank's review. Boom. Just find, here we go. So people, for sure, there's an awful lot of experimental work and very few transport modelists in perovskites. I think, Jarvis, you would agree with me on this point. And so there's a big gap in the market for modelers, simply because people have done tons and tons of experiments on it, but because they don't have a model that really fits, because these things are so complicated, it's not well known. But I mean, they've got some very useful experiments, which is what's reported in this review, with various different types of spectroscopy, that at least can identify how big these grains are. And also, if you look at that review, it does discuss the extent to which it's understood how much ion transport occurs along these boundaries.
Say, for example, you said several times that the ions are segregating the grain boundaries.
Yes.
Is that shown by anything like yields or?
Yes, that's the point. Yes, it is shown. There's a lot of experimental evidence which is reported in this review, which I wouldn't say it nails it completely, but it's strongly suggestive of that behavior.